when the wafers are brought into contact. We'll see that as well later on when we actually do the bonding. Right, software. Alright, just while we're still on the hardware side of things, this is the handle for the wafer clamp, which I showed you from underneath, but you can see it more easily on the top. Turning that will release the wafer, retracts the clamp, releases the wafer. So after the bond is complete, you'll retract the wafer clamp, move the manipulator down, the bonded pair will then drop down onto the lower platen, separate away for cooling, and then you can take it out of the machine.
Is there a way, like, accidentally, if someone touches this, would it release the wafer?
Touching it, no. You would pretty much have to deliberately open it. It's not really possible to accidentally knock into it and open it. It's quite the spring force inside there is fairly substantial. You have to do it deliberately. These, when the leveling position is set, they have these locks on the top. So those can't really be accidentally adjusted either. So to do the leveling, we need to loosen off these locking knobs on the top. Then we can turn it to adjust the leveling. I taught you through the leveling procedure is a whole talk in its own right. So I'll talk you through that later. And then lastly on the lid, we have these two feed throughs. So this is the electrical feed through. This sends the power for the plasma, the power for the bonding voltage, and the power in and out for the upper heater. And in here is a thermocouple, so that's just for monitoring the temperature of the upper platen. All of those cables are fed through this chain and then they go off, they spread throughout the machine to wherever they need to go. Okay, that's pretty much a brief introduction to the hardware side of things. Does anyone have any questions on hardware?
What are these screws?
These screws, yes. Good question. They are for clamping the lid down. So we just need to use a standard Allen key to tighten those in. Unfortunately, it's a somewhat manual process.
So this is like during the bonding we have to do?
After you've loaded the wafers, you'll close the lid, you'll bolt these in immediately after that. That will ensure that the lid is pulled down flat. And they also serve a second purpose, which is if we're applying high force for any reason, if you're doing, say, a eutectic bond or a thermocompression bond, and you're applying 25 kilonewtons of force, it stops the lid from being pushed open. Because it's possible that with that amount of force pushing up, if you didn't have them in, it would overcome the vacuum, the force of the vacuum pulling down, open the lid, vent the chamber, and basically cause all havoc to the turbo pump. So they're there, they're important for that, to keep the lid sealed down when you're applying force. So I recommend that they just put in all the time. So close the lid, put them in, and then operate, and you're going to have no problems. It's also possible that if they're not in and you try to start pumping down, if there's a slight gap around this edge of the lid, that's possible to occur because the lid pivots on the side there. So as that comes down, if it hasn't quite contacted on this side, there might be a little gap, and then the chamber will not be able to evacuate, it won't be able to pump. So it should be pumping a leak through there. So the clamps help to make sure everything's sat flat, sealed properly before you start pumping out. So yeah, I'd recommend that they're used all the time. Good question. Anything else? I think I've covered most of the other things.
Where's the power supply with?
Which power supply? The mains. The 500 volts. Okay, there are two high voltage power supplies. They are not really accessible, but one of them is located underneath the PC here, which is for the plasma system, and one of them is located on a sort of rail system mounted that way. You can just see the high voltage one. So that's just there. That you can see the edge of that griddled box. That's the high voltage supply for the bonding voltage. So that power supply can deliver 2,500 volts, and the one for the plasma system, which is underneath at the back there, can do 500 volts. If I show you, I've got a diagram of the electrical hardware, which I can maybe show you. That might be useful. Yeah, so this is the model of all the electrical hardware. This box here, that's the bonding voltage, 2,500 volts that I just showed you under there. 24 volt power supply. Some circuit boards are inside these boxes for controlling the high voltage.
There's a transformer over here.
There's a kind of internal transformer inside that. In front of that there is an isolation transformer. That's to isolate the upper heater circuit from ground. So the upper heater circuit is floating. So in the event of a high voltage short to the upper heater, the whole heater system will just float up to high voltage. It won't short out or blow anything. Two further transformers, upper heater, lower heater. They step down from mains voltage to about 85 volts. 85 volts open circuit, 75 volts closed circuit. Terminal blocks for connecting the transformers. Heater circuits, so these are interlock relays and controllers. A series of circuit breakers. If anything trips, you can open this panel. They're accessible through a little slot. That's all you'll be. Yes, yeah, that's all you'll be able to see is what those are. So you can just flick them back on if needs be. And then at the top we have terminal blocks. Blue and white is for mains power. So they distribute, one mains feed comes into those rails, then that distributes power to everything else inside the machine. Black and red is for 24 volts, so that this power supply feeds those black and red, and then they in turn feed everything else that requires 24 volts. And then lastly there's a mains contactor, so when you first plug the machine in, there'll be 24 volts applied to these switches. Push the on switch, the 24 volts will then be used to latch this contactor, which then brings in the mains voltage to everything else. And two surge protectors. So in the event of, say, a lightning strike or any voltage surge, these will cut in to protect the rest of the system. In this case, mains voltage is approximately 246 volts, which is what's being output by this chap. So yeah, because the machine's built to European specs, UK specs, it requires between 200 and 250 volts, and your supply is 110 volts, so we're using this step-up transformer to power the machine without any modifications to anything else.
Is it the same option if you get the transformer?
Sorry?
Is it like an option when you bought this that we get the transformer? Is it similar to this or?
Yes, I don't think you bought that option though, so this is your transformer that we found on the shelf over there and then rewired it to work for our purposes. But yeah, there is an option available from AML to purchase this transformer. Although, I think the way it works is that because the transformer that we supply is manufactured either in the US or in Canada, it kind of doesn't make sense for us to buy it, have it shipped to the UK and then ship it back to the US again. So I think we would have it shipped directly to your site if you did purchase that option. But there's no need to, because you had what you needed to do the job here and it's working fine. I've done extensive testing yesterday and everything works perfectly. So this is a good piece of kit, does the job nicely. Okay, anything else on hardware? Nope. Good. We'll probably touch more detail on everything if I've missed anything as we go through, as we start operating the machine. So, that's closed down. Software is all written in LabVIEW. We've got 3 separate programs. The shortcuts for them are here. So there's a configuration program, a control program, and a log file viewer. For operating the machine, you'll be using the control program. If you need to do some data analysis or something's gone wrong and you want to analyze a data log file, the log file viewer helps to display everything graphically rather than looking through a tab delineated list of numbers. That's not very helpful. So you can view it as a graph with this log file viewer. Configuration program is for machine setup. It's mainly used by us in the factory, but there are a couple of things that you maybe need to adjust later. So I'll start by talking you through everything in the configuration program. Okay, so when we first open it up, it's going to ask you for a password. The password is AML. If you're ever asked for a password, everything is AML, pretty much. There are higher level passwords as well. I'm going to use the higher level password at the moment so that I can show you everything in there, but you won't need to use it, so I'll just give you the AML password. Okay. So yeah, the AML password gives limited access to this, and it will only allow you to change things that you are going to maybe need to change. More advanced things that we don't want you to fiddle with are protected by a higher level password. So this vision, and we've got various tabs across the top of this for configuring different things. First one is vision and motors. So the options we've got are this vision system. These cameras are made by Basler, so that's the Basler vision system. Pliora is for legacy support for older machines. They're the cameras we used before this, and Bobcat NIR is an optional upgrade. So for bonding to silicon wafers, I mentioned earlier we have to use IR illumination. These cameras are sensitive to infrared light to within a small range. The NIR cameras are sensitive over a much wider range. And that's useful because as you heat wafers up above 40 degrees, they become IR opaque. So these cameras can then not see through them if they're heated. So we have a couple of customers that needed to do hot bonding, and they needed to be able to do alignment with hot wafers. So they need this NIR cameras that can view over a much wider range of IR transmissions. Not applicable to your system, but that's why the option's there. We've got some tick boxes here. Motorized X, Y, and theta. All of our systems are equipped with motorized X, Y, and theta controls nowadays. Older machines weren't, so that's tick boxes there for legacy support again. Motorized Z is an option, so at the moment approximately 50% of machines are equipped with it. This particular one is. So I mentioned earlier on there's a motor down there. This one. That drives the Z actuation, the hydraulic system. There is also an option for a manual version which has a big kind of like a submarine hatch wheel that you have to apply force with it manually. Motorized option is a lot better, so you've done well to get that. So that's ticked. Motor system, we've got two different control systems. For older machines have EPOS 1 control, this machine has EPOS 2 control. So that's what this option's for. You won't need to ever change any of these, so I'm just talking you through for why they're there. Absolute X, Y, theta encoders. This machine does not have those. That's a kind of development feature that we're working on, so that option is in the software for our development team to be able to use those. And software controlled illumination. Older machines didn't have illumination controlled by a slider in the software. They had pots on the front panel here. So we have to have that option in there for supporting the older machines. Your machine does have software control there. Inside this configure button, we've got a separate screen. Two separate screens, in fact. So this is the same as the screen that we're going to see later in the control program, so I won't talk through too much detail now, but we've basically got the vision feed from the left and the right camera there, and then some controls for the motors, such as step size, speed, and setting home positions and this kind of thing, which I'll talk you through later. General configuration. These are some fairly low-level parameters that we don't want you to adjust. These are things that we set in the factory. They're kind of calibrated to this particular machine. It's to do with the number of encoder counts for the motor that correspond to 1 millimeter of movement, say, so that when you ask the software to move it by 10 microns, it will actually move it by 10 microns. Encoder calibration. This encoder here, that's how the software is able to tell what height the manipulator is at. So how far, and it uses that height to calculate wafer separation. The response from each of these that we buy in is slightly different. So we measure those versus a micrometer, plot the graph, get the calibration coefficients, and they go in here. Z limits, these are important. We don't want you to adjust these. So the upper limit is set to prevent mechanical clashing of any parts of the manipulator. So behind this brace bar here, there's a plate which is attached to these sliders, and the upper limit is when the plate underneath here collides with this plate at the top. So that value's been set with a feeler gauge. So at half a millimeter, when they're separated by half a millimeter, the software will stop the manipulator moving any further to prevent mechanical clashing, to protect the system. Lower limit, that's simply when the chamber internal stack bottoms out on the bottom of the chamber. So you can't go any lower than that. So again, it will just have a warning, say you've reached the lower limit. And that lower limit is determined by this number. Powered lid limit. The lid is interlocked, that you can only open it or close it when it's safe to do so. One of the conditions that is required for it to be safe is that the platens are separated, because in actual fact the lower platen can overlap the position of the upper platen, and if it was higher than the upper platen, if you try to close the lid, they're going to crash. So it forces you to have the lower platen lowered sufficiently to make it safe, and that's determined with this number. Backlash compensation is not really relevant on your system. We do have as an option an automatic alignment. Now the motors have a certain amount of backlash in them, between 5 and 10 microns usually, and the automatic alignment needs to know what those values are to be able to take up that backlash before it knows that the manipulator is going to start moving. So we put those in anyway, but in this particular case they're not relevant here. Pixel scaling. Again, this is for automatic alignment. Essentially, 1 pixel that these cameras show you is equivalent to 1.16 microns, which is scaled up to 400 out of 465. So you can resolve 1.16 microns. So essentially, we have to be able to move by 2 microns before you're going to see a 1 pixel shift on the screen. That is necessary for the software to be able to calculate positioning to do automatic alignment, but it's not necessary for this system. Okay. Serial tab. So there's 4 different systems that communicate with the computer via different serial ports. The motors are attached directly to a serial port on the computer. The rest of them are attached via USB adapters. These are just the COM ports that each system is attached to, so the software knows where to look to initialize a connection to each system. Don't change them, otherwise all that's going to happen is that the software can't communicate with, say, the pump or the motors, or it'll just lose communications and you won't be able to use it. Okay. HT, so this is the high voltage bonding voltage. We have an option to not fit that. You have got it fitted because you're going to do anodic bonding. Some of our production customers only ever do one type of bonding. If they don't do anodic bonding, they don't need the power supply, so it's not fitted. So hence we have the tick box there. Power supply type, yours is equipped with a Spellman power supply. Older machines, this was from a different supplier, so the software needs to know which one is fitted. Then there are some calibration factors. So this is to calibrate any mismatch between the power supply and the PLC controller. So essentially, with those calibration in place, we've used a calibrated meter to measure the voltage on the input side of the lid, and it's calibrated such that when you ask for, say, 500 volts, you get 500 volts. You don't get 505 volts or something like this. So any mismatch is taken up using these parameters. Yeah, we've calculated those parameters in the factory, so you don't need to change them. RAD, the plasma system. There's 3 options. We have either fitted, not fitted, or software controlled. So some machines that don't have the plasma system have not fitted. Older machines, it was accomplished with a kind of manual control. So up here there was a toggle switch, a couple of LCD screens, and pots for setting the voltage and the current. Modern machines like this one is all it's all controlled via the software. So yours is software controlled. Similarly, we have other parameters. These first 4 are for their scaling parameters, so that when you ask for 500 volts, you get 500 volts. When you ask for 100 milliamps, you get 100 milliamps. The default voltages for this system is 500 volt, and the default current is 100 milliamps. So all that means is that when you go into the program, those values will be already put there for you. So essentially all you need to do is turn the system on and off. But you can adjust it if you want from inside the software. You don't need to adjust the defaults. Maximum power supply voltage is 500 volts. A maximum power supply current is 200 milliamps. So if for some reason, in the event of a voltage breakdown, say, the software detects more than 200 milliamps, it will shut down the power supply to prevent any damage to it, because that's the specification that Spellman give us as the maximum that it can output. Some tolerances and some settling times. So the settling times are there to give the plasma time to strike and stabilize before any errors or warnings come up. You may see when you use the plasma if the voltage draws